Hi, I wanted to create a short video on discussing some of the concepts behind thin lenses and images created by thin lenses. I will do kind of a quick conceptual review of thin lenses, and then we will go into the computer simulation and discuss and make predictions about where the objects will be located, where the images will be located, and the magnification. And we will also discuss some everyday applications for different types of thin lenses. So I'm going to share a whiteboard. And in this chapter, we will go over two types of thin lenses. One of them is called a converging thin lens, and one of them is called a diverging lens. In the first case, a converging lens does exactly what it sounds like. It takes light and it converges it to a focal point. And the reason why it does that is because of the way we learned about light and how it refracts through different materials. So if this is a piece of glass, for example, a converging lens is thicker in the middle and thinner on the ends. And so if a light ray comes in right in the center of this lens, the light coming in, it hits the center, and notice that this is a right angle. So if it hits at a right angle, the light will not bend at all as it passes through from air to glass, and it will just go straight through. And the same thing will happen when it goes from the glass back out into the air on the other side, because again, this is a right angle. So any light that hits directly in the center will not refract, it won't bend at all, it will just pass straight through. But if you look at one of the light rays hitting the lens here, notice that it's no longer hitting at a right angle anymore. So it's not just going to pass straight through. In fact, what's going to happen is, here's the normal to the surface, right? It's always perpendicular to the surface. The light is going to bend towards the normal as it passes through this material, and then when it goes from glass back out into the air again, if I draw a normal to the surface here, it's going to bend away from the normal even more and hit here. And you could do the same thing for a light ray on the bottom. It bends as it passes through the material, and the amount of bending depends upon the properties of the material itself and the shape of it. But the light will converge here, right at this point. So a converging lens, thicker in the middle, thinner on the ends, it takes light and converges it to a focal point. On the other hand, a diverging lens does the opposite. It takes the light and diverges it. So similarly, if I have a light ray coming straight in the middle, if it hits right here, it's hitting at a right angle. It's not going to refract at all. It'll just pass straight through, hits at a right angle again, and passes straight through. So that's not very interesting, but let's see what happens when it hits somewhere else. So notice that the diverging lens is thicker on the ends and thinner in the middle. So the normal to the surface looks kind of like that. And so the light ray will bend. As it goes into a higher index of refraction, it bends towards the normal. Sorry. And then it goes back out into air into a lower index of refraction. It bends away from the normal. Okay, so it keeps bending out as it passes through this diverging lens. The same thing will happen down here. And so on this side of the diverging lens, the light never converges to a point, right? It just keeps diverging out. And so the light rays appear to they would appear to converge at a point back here, behind, on the other side. So that's the difference between the two lenses. One of them converges the light, one of them diverges the light. Okay. And a converging lens, its we're going to use the lens equation like we learned with mirrors, 1 over p, which is the object distance from the lens, plus 1 over q, which is the image distance, where the image is located, equals 1 over f. We can apply this equation to the thin lenses as well. I won't derive it. If you're curious, the book will do it for you. But for a converging lens, the focal length is a positive number. Whereas for a diverging lens, the focal length will be denoted as a negative number because the light that is diverged is over here, but the image is on the opposite side of that diverging light, right? So it's a negative value for the focal length. The converging lens, the light that comes through the lens is over here. It's on the right side of the lens. The image is located on the right side of the lens. So it's a positive focal length. Okay. So just keep that in mind when you're setting up your equations for converging versus diverging lenses. Okay. We can also still use the magnification equation, negative image distance divided by object distance, p. So let's take a look at the simulation and see what it looks like for converging lenses and diverging lenses. Here's the simulation. Last time we were working on mirrors, this time we're working on thin lenses. So I'm going to turn the light rays off and I'm going to zoom in. So notice that here's my thin lens and this is a converging lens. The radius of curvature is 120. There's something a little bit wrong with this simulation because it's saying that the radius of curvature is 120, which means that the focal length would be half of that, 60 centimeters. But it's putting the focal length at 120. So I just want you to be aware that there's a little error here. The focal length is 120 centimeters here. This radius of curvature should actually say 240. So just FYI. I don't know why there's a problem with that, but just be careful when you're doing the lab. But notice if I get really, really far away from this lens and I put an object all the way out here and I turn the light on, notice that the light's going to come in, it's going to hit the lens, and it's going to converge at the focal length over here. The real light is over here that's leaving the lens and it's forming a real image right here. So this would be like taking a magnifying glass and having sunlight from the sun, which is really far away, come in. All of that light from the sun is going to converge at the focal point right here. And again, it get really hot, that point. If you take a look at the diverging case, if I put the object really, really far away again, the light rays will come in and they will diverge completely on the other side over here. The light rays never form an image on this side of the lens, but it does appear to form a virtual image on this side of the lens, on the other side. So if I take these and I extend those light rays backwards, it appears like the light is basically converging at this point in space. So it's a virtual image because the light rays are actually diverging out on the right side of the lens, but the image is a virtual image that is actually being formed on the left side of the lens. Excuse me. So let's look what happens for different situations for a converging lens. Let's suppose we put the object, I'm going to turn this off. Let's put the object out here outside the focal length of the lens, and let's put it at 160 centimeters. Okay. And let's make a prediction. where's the image going to be located? Is the image upright or inverted? And is the image real or virtual? And is the image bigger than the object or smaller than the object? Let's use our lens equation. 1 over P plus 1 over Q equals 1 over F. The object was located 160 centimeters away. I'm looking for the image distance Q, and the focal length was 120 centimeters, even though it's slightly wrong in the simulation. If I solve for Q, that gives me 480 centimeters. It's a positive value. And if I solve for the magnification, which is negative Q over P, it's a negative 3. So what are these numbers telling me? The image is a positive value. So that means that the image is being created on the side where the light comes out, and it's a real image. The magnification is a negative 3. So the negative is telling me that the image is inverted. So it's upside down. And the 3 is telling me that the image is 3 times bigger than the object. Let's see if that's what happens in the simulation. I will turn the light on and we will see. I zoom out a little bit so you can see where the image is. So notice the image is inverted, that's what we predicted, and the image is bigger than the object, which is also what we predicted. The object is 20 centimeters high. The image is 60 centimeters high, so 3 times as big, so that's what we predicted, and it's inverted. And the image is located, what did we predict? 480 centimeters, so that's about right where the image is away from the lens. So that prediction works out. So what is an everyday example of this kind of lens? Notice that this lens is projecting a real image. The image is inverted. So the best example of this that I always use in everyday life is a projector, like in your classrooms. A projector uses a lens that actually takes an object, right, and it projects it onto a screen. Okay, so the image is actually projected onto a screen. The image is a lot bigger, right? If you've ever used like an old school slide projector, I don't know if anybody is still familiar with those, but there are these tiny little slides, like slides of pictures, right? And you would put them in the slide projector, and the slide projector would project the image onto like a wall so you could see a bigger picture. You had to put the slide in upside down so that when the image was projected onto the wall, it was projected the right side up. So sometimes you'd put the slide in the wrong way, the image would show up inverted upside down, so you'd have to flip it around. I don't even know if anybody uses those anymore, but my parents used to have them. But most the thing you can think about is if I need to project something onto a screen, I'm going to use a converging lens, like something like this. Let's look at what happens if I put the object inside the focal length. Okay, so I'm going to turn the light off. Let's zoom in a little bit. And let's suppose I put the object at 80 centimeters away from the lens. So I will put the object now here. Let's make a prediction of what will happen now. Where is the image located? Where is the, and is the image real? Is it inverted? Is it virtual? What's going on? So let's bring the whiteboard up. I changed the object distance. The focal length is still 120. So let's see what happens now. Sorry. Object is at 80. Oh my gosh. I just want the pen. Okay, the object is at 80 centimeters. Focal length is still 120. So if I solve for the image distance, I get negative 240 centimeters. And if I solve for the magnification, it's negative 240 divided by object distance, which was 80. So this is positive 3. So what do these numbers tell me? So Q is negative. That tells me that the image is going to be a virtual image. Okay, so the light that leaves the lens is coming out on the right side of the lens, but the image must be being created on the left side of the lens. And the magnification is +3. Okay. That means that the image is upright, and because it's positive, and it's 3, so it's 3 times bigger. So let's see if that's what happens in the simulation. Turn the light on. Okay, so this is where the image is located. 240 centimeters away from the lens. That's exactly what we predicted. The image is, the object is a little bit over 20 centimeters. The image is almost 70. So it's about 3 times as big, which is also what we predicted. So the image is being formed on the same side as where the object is, and it's on the opposite side of the light that actually leaves the lens. On the right side, the light never converges. It never forms a real image over here on the right-hand side. But if I take those light rays and I extend them back, it appears like the light is coming from behind the lens. So what is an example of this? This would be an example of this would be a magnifying glass. When you hold a magnifying glass, you put a book right behind it. So the book would be the actual object right here. The light from the book passes through the lens. It doesn't converge over here, but it appears to converge behind the lens, and it's bigger and it's upright. So the image of the book has been magnified behind the lens. Okay. It doesn't create a real image, it creates a virtual image behind the lens. So converging lenses can create real images like this that are inverted. They can also create virtual image like this in the case of a magnifying glass. Now let's look at a diverging lens. Boop. Okay. Let's turn on our light. Let's turn on our light from our object here. Notice that the light hits the lens and diverges out. There is a virtual image being formed here. And let's drag this thing around and see what happens. Notice that no matter where I put the object, it's always creating a virtual image. So diverging lenses only create virtual images. Let's set up a situation and make a prediction about where the image would be located and its magnification. So let's put the object at 140 centimeters away. If I work through the math for this, let's do that. I put the object 140 centimeters away. I'm trying to figure out where the image is located. This is a diverging lens. So if you remember, for a diverging lens, the focal length is negative. So I will put negative 120 here. Q ends up being it's about negative 65 centimeters. So that means that it's on the opposite side of where the light is diverging out from the lens. It's on the same side as the focal length of the lens. And the magnification is a positive number in 0.46. Magnification is positive. That tells me the image created is upright. And the magnification is less than 1. So the image is going to be smaller than the actual object, about half as big. Let us see if that's what happens. Let's turn the light on and observe where the image is now located. So the image is a virtual image. It's on the same side as the focal length of the lens on this side, and it's about 65 centimeters away from the lens, which is what we predicted. It's upright, which is what we predicted, and it's about half as big. So the original object was 20 centimeters away. The image is about 10. So that matches our prediction as well. Diverging lenses are most commonly used. The best example I can give for diverging lenses are when they are used in eyeglasses. I am a nearsighted person. I can't see things far away. They are blurry to me. So my glasses are actually shaped like a diverging lens. When I put my glasses on, my eye would be like right here, right? And maybe this is the object that I'm trying to look at. Okay. The image that I see when I look through this diverging lens is actually closer, right? So the diverging lens takes the object and makes an image of it that is actually located at the focal length for my eye so that I can clearly focus it. So that's what, when diverging lenses are used, that's the most common example I can give for diverging lenses. Okay. They create a virtual image that your eye will be able to focus on easier than something really far away. So that's my quick crash course on thin lenses and the lens equation and predicting where the image will be located and the magnification. I hope this helps. I hope this helps with your lab report, and I'll see you soon. Bye.